So friends, to see the demonstration of my principal component analysis app, you need to go to my website datapundit.in. Here you need to click on this MagicPCA option, which will lead you to username and password interface. I'm entering my username and password. You need to get access for it if you want, and it is paid access. We can work in a manner which is most suitable to you as well as me. So this is the interface for the app. It can be customized for different users. Currently, this is the way I like it. That's why it is like this. I am uploading the data set which I want to analyze. So this data set contains information about various excipients and Hansen solubility parameter values for those excipients which are calculated for indomethacin. And it also reports the differential scanning calorimetry results for mixture of these excipients with indomethacin. Basically, the researchers are trying to predict the miscibility of indomethacin by using the Hansen solubility parameters. Why it is so? Because miscibility is very important factor for considering hot melt extrusion as an option for solubility improvement. So that is the reason these researchers are interested to know if they should use particular excipient along with indomethacin so that they can improve the solubility of their API. Now, to get going, we need to click on this column which contains categorical information. Categorical information is information which is present in the form of text. To group data into different classes using principal component analysis, it is mandatory to have certain categorical variable in your data set. One of the other requirements which is necessary for you to get going is that your data should be in CSV format. Also, it should have unique row names and unique column names. Then only you will be able to successfully import your data set into the app. Once you select this column by clicking on the bottom header here, you can get correlation matrix, which shows interrelationships between variables in the dataset. Now here you can see that all the diagonal elements are highly correlated. That is natural because it is each variable related to itself. Hence, it is naturally going to have correlation coefficient of 1. But if you'll hover over these these variables, you will get to see correlation coefficient for each variable, and on the basis of the value of this variable you can come to know what is the relationship between these two variables. So let's say, for example, now you can see that polar forces and hydrogen forces are positively correlated as their correlation coefficient is 0.63. They would be negatively correlated if the correlation coefficient was minus 0.63. And since the correlation coefficient is closer to 1, we say that they are slightly related. If it was less than 0.5, we would have said that the relationship is not that strong. Here we can see that volume-dependent solubility and dispersion forces are also positively correlated. There is a good degree of interrelationship between all these factors, which is good to get a good principal component analysis. Now my app can segregate training and testing data on the basis of training set probability input provided by the user. So by default, this training set probability is set to 0.59, which is close to zero point 0.6, which means that I can expect close to 60% of my data to be present in training set and close to 40% of my data in testing data set. Now it has automatically got divided into training and testing data set. All I need to do now is just click on the training data set and again select on the categorical variable here in the training data set. If I don't do this, I don't get a nice bar plot, which I'll show you later. If my data was spectroscopic data, I would have been very happy to look at this plot. But since my data is not spectroscopic, I can choose not to see it. If I go to Visualize tab, here I can see box plot for each column. I can see that there is great degree of variation between hydrogen forces, and they are also not normally distributed. As of now, I'm not going to do much with it because the data source is a research article. If I click on the model tab, I get to see the summary of my model. Now this summary says that this model was built using 4 principal components, and the standard deviation for this model uh, went on decreasing as the number of principal components were increased. That it also says that only the first principal component, that is PC1, was capable of describing 75% of the model, whereas PC2 added 16% information to first principal component, which means that if I add the total information which was added by principal component 1 and principal component 2 was 0.92. So this is cumulative proportion of variance explained by each principal component. Now we would like to have our model where most of the information is described by first few principal components, and those principal components should ideally be able to describe 75% of the model. In our case, it is 92%, hence it is a good model, and we can proceed to see the biplot. So this is the best feature of this app. Here you can see that the data points are divided into soluble, that is yes and no, kind of two groups. So the yes group contains excipients which are miscible with indomethacin, whereas the Y group contains excipients which are not miscible with the indomethacin. This plot also tells us what is responsible for dividing these samples into these two groups. If we look at these loadings, which relate to polar forces, hydrogen forces, volume dependent solubility, and dispersion forces, it shows that with increase in all these properties, the excipients are getting classified as not soluble, not miscible, whereas with decrease in these properties, the excipients are getting classified um, as miscible. So this is reconfirmation of Hansen solubility parameter. It is one of the parameters which is used to predict compatibility between two materials. So it generally says that if the differences between forces is less for two materials, then they are more compatible. If the differences are large, then they are less compatible. So this is reaffirmation of the same principle, which is very good. And we can also look at the explained variance plot. This explained variance plot tells us the same story which our model summary tells, but only different thing which is available here is this graphical representation. It shows us elbow pattern, and we can see that after the second principal component, uh, there is a slight elbow formation, which indicates that after second principal component, there isn't significant addition of information when number of principal component is increased further. So this means only two principal components are good enough to classify our samples using this model. Now we can, accordingly, we can adjust the final numbers of principal components in our sample, in our model. Here we have option to change the final number of components. I am going to keep them to 2 depending on my analysis here. Now if I look at this, um, sorry, I will just clear this. Now this is training prediction summary for my uh, for the training data set. So what we have done here is we have used the model to predict the class of each and every data point present in my training data set. So if the actual value of DSC test is yes, then it has predicted it as 2, and if the actual value is no, it has predicted it as 1. So every yes means a 2 here and every no means a 1 here. But remember that it will have some error, it will not be um, so accurate. So in this case we can see that if we look at the classification summary, we can see that it has classified 7 samples as not miscibles and 15 sample as miscible. There is not even a single error. If there would have been an error, if there was a possibility of a sample being immiscible, but yet it was wrongly classified as miscible, then it would have been reflected here. If there was a possibility of sample being um, immiscible, but it was predicted as miscible, then it would have been reflected here. So all the misclassification would have been reflected in the places which are marked. If you want to see individual results, you can always go for these classification tables. Now we have only 22 samples, hence it is very easy to spot the result for each and every observation. But if we would have 100,000 or more data points, then it would be difficult. In that case, we would prefer to see classification summary. Now, we can also see classification accuracy, which means we have classified 100% of the samples accurately. There is not even a single error, and which is reflected in our classification error as well. Just like train set predictions, we also get test set predictions. Here, we get results for each and every test set um, data, data point. Here we can see that what is the actual result from differential scanning calorimetry. and what is the predicted result. So now if you have this model, you don't need to perform DSC every time. You can actually predict the result of DSC. If you look at the classification summary, you get to know what are the number of misclassified samples. So there is one sample which was immiscible but has been classified as miscible, and there was one sample which was miscible but has been classified as immiscible. So you can also see the classification accuracy here and classification error, which is okay. Now, if you want to predict the differential scanning calorimetry results for unknown samples, now on, you don't need to perform it again and again. Even if you have thousands of such excipients uh, for which you will want to perform DSC, you can simply upload the data related to their Hansen solubility parameters here, and you can simply do guesswork on the solubility for those parameters. Let's say I have uploaded this data here. Now I have to also upload possible classification here. If I don't upload that, I don't get actual classification results. So if you do not know the exact class of each and every data point, it is okay, but you should label it. You should just write some class there, and some class in the sense the same class which was there at the time of model building, and that class has to be labeled here. You need to mention all the classes which were present at the time of model building. So in our case, there were two classes present, hence I need to randomly label each and every data point as no or yes. Then there is an option to save the model file. So if in future I need the model file, I don't need to perform analysis again and again. I can simply click here and save my file. I have already saved my file. So I will upload the file here. Now the file is uploaded. And now I can check the classification result for my model. So there's some change in the model file. So I'll upload my file here. I'll just use the new file instead of using the old file. I'll just use a new file. So here I'm going and I'm again uploading my model. So this model has been uploaded, and now I see the result for each and every component. Now you can see that it does have this actual component, but it need not be that accurate because you have guessed the result and you actually don't know. This might be useful in cases where you are trying to classify raw materials and you already know that your vendor is selling it by saying it to be some particular material. Let's say your vendor is saying that he's selling you oak wood, and then you actually go on and check if it is really oak wood or not. So like that, it might be useful in those cases. And in this case, it could have been the miscibility prediction on the basis of Hansen solubility parameters versus miscibility prediction on the basis of differential scaling calorimetry. So it can be anything. And I hope it will be useful for you in your research. And there would be many more such interesting applications of principal component analysis, and I'll be happy to help you with them. So if you're thinking of some research study using principal component analysis, feel free to get in touch with me. and maybe we will work our way around it. Thank you so much.